purpose of this lab is to use a Ruben's tube setup and the relationship between speed, frequency, and wavelength to calculate the speed of sound in methane gas. We also verify the equation for the speed of sound in an ideal gas. The Ruben's tube is named after an invention of Heinrich Rubens. A tube is perforated with a row of evenly spaced, evenly sized holes at the top and covered with a flexible membrane at both ends, in this case a metal cap and some Glad seal. The gas is pumped into the tube and speakers are put at either end. Their height depends on the size of the holes and the pressure of the gas from within the tube. The areas of rarefaction have a higher pressure inside and push gas outside, while areas of compression have lower pressure inside, so the gas remains inside the tube, causing a smaller flame to occur. We can use this in order to measure the wavelength of a wave, and then, using the equations v equals f lambda, find the velocity of the speed of sound in methane gas at room temperature.
Materials and equipment. 3 foot long, 2-inch diameter, open metal pipe.
Drill bit, 1/16 inch.
Flat iron cap.
Mylar or Glad seal wrap.
Speaker.
Hose barb.
Propane / methane / flammable gas.
3/4 by 4 feet wooden board.
Rubber tubing.
Fire blanket.
Fire extinguisher. Set up the apparatus as shown in the diagram of the experiment, with the speaker at one end of the metal tube and a metal cap at the other end. 2. Light the metal tube on fire. 3. Once the Ruben's tube is on fire, send a simple frequency sound wave using the speaker. 4. Observe what happens and note it down. 5. Send another sound wave and measure the wavelength. Record. 6. Record the frequency of that sound wave. 7. Calculate the speed of sound for that sound wave. 8. Repeat steps 5 to 7 4 more times.
Equations. V equals lambda f. C ideal equals the square root of gamma times Boltzmann's constant K times temperature over m, the mass of a single molecule of the gas. The average speed of sound in methane gas was calculated to be 454 meters per second. The actual speed of sound in methane gas is 460. Our data was fairly close. Then we calculated the percent error for each individual trial using the equation measured minus actual divided by actual. For trial 1, a percent error was found to be 8.15%, trial 2, 0.88%. Trial 3, 0.31%, and Trial 4, 1.70%. This lab was used to demonstrate the idea that all sound waves have the same speed using a fun experiment called the Ruben's tube.
A sound wave is sent through the metal tube that is lit on fire, and the flames form waves that resemble the sound waves. Using the relationship velocity equals frequency times wavelength, the speed of sound can be calculated.
Hypothetically, this experiment should have ran without any prompts and should have given an answer close to the expected speed. However, due to the different sizes in the holes made, the amount of gas available for the flame varied. This made it impossible for a perfect sound wave to be seen and thus calculated. Another reason our Ruben's tube was not completely successful was because the speaker used to send the sound wave did not have a powerful base, and thus the vibration was minimal, which was key to producing a sound wave. We believe that fixing the size of the holes and adding a speaker with a better base will resolve the problems and create a better experiment.
A source of error that we are measuring is that we are measuring the wavelength of a flame using a ruler, and because we are naturally afraid, we won't measure the wavelength accurately. Also, another source of error is that the sound wave is ideally expected to be constant and reach the opposite end of the metal tube, thus producing a standing wave, which might not necessarily happen perfectly.